Okay, so in this lesson, we're going to be going over the fundamental theorem of calculus, as well as the mean value theorem and the average value theorem. Also, we're also going to look at the second fundamental theorem of calculus, and we're also going to look at what's called a net change theorem. Now, all of these theorems, they may sound complicated, but they all tie together, and you're going to see that, and they're very, very useful for pretty much all of the topics and essential, applications that you're going to be doing for the rest of, not just Calculus 1, but Calc 2 and Calc 3. So really take your time looking over the notes and making sure you can do all the practice problems correctly, because it's really going to help you throughout the rest of the course. And you're actually going to find it's not that hard. So let's look at the first theorem, which is simply known as the fundamental theorem of calculus. Now, it's with this name, you probably guessed, it's pretty much the most important theorem of all of calculus, because it allows you to essentially evaluate a definite integral. So what it says is that if you have a function that's continuous on a closed interval a, b, and you have that large f is an antiderivative of small f on the interval, then you can simply find the integral of small f of x from a to b by evaluating large f of b minusing large f of a. So it's just a difference of, large f of b minus large f of a. So it actually becomes almost like an algebra problem. And it's going to actually simplify and save you a lot of work that you've been having to do to, calculate areas between, curves and, functions and all that. So let's go through a couple of examples, because you're going to see how it exactly works when you're using it. So we're going to evaluate each of these definite integrals. So the first one we have the function x squared minus 3, or not the function, but the integrand. So let's find the antiderivative of x squared minus 3, which will be x cubed over 3 minus 3x. And the notation we like to use is, doing like a one-sided bracket from 1 to 2. And that tells you that you're going to be evaluating this expression for 2, and then you're going to be subtracting it from when you evaluate it for 1. So in other words, it's going to look like this. 2 cubed over 3 minus 3 times 2 minus 1 cubed over 3 minus 3 times 1. And this is just algebra. So this will just be 8/3 minus 6 minus 1/3 minus 3. 8/3 minus 6 minus 1/3. So this will be 8/3 minus 18/3. So this will be negative 10/3. Minus, I need a little more space here, 1/3 minus 3. So 1/3 minus 9/3. So minus negative 8/3. And you're going to get that we get negative 2/3 as our answer. And that's it. Let's look at the next one. We have the integral of 3 square root of x dx from 1 to 4. So remember, this is the same as 3x to the 1/2 power dx. So the antiderivative of this will be 3x to the 3/2 over 3/2. And again, we can use this notation. Sometimes you could just use a vertical line. I usually will use a bracket to make sure I don't confuse it with something else. And we put 1 to 4. We're going to evaluate this at 4 and then subtract from it when we evaluate it at 1. So simplifying this, let's first, rewrite this as 2x to the 3/2 1, 4. And I might just go across here just so it doesn't look so confusing. So we plug in 4 first. So we have 2 times 4 to the 3 halves minus 2 times 1 to the 3 halves. Now let's remember your algebra. 4 to the 3 halves is just 4 to the 1 half times 4. So this is just 2 times 4 times 4 to the 1 half. Because remember, that's just like 4 to the 1 times 4 to the 1 half. And 1 to the 3 halves is easy, so it's just 2 times 1, so minus 2. And then so this is 2 times 4 times 2. 2 times 4 is 8, times 2 is 16. So 16 minus 2, and your answer will be 14. And then now for C, actually I can crank this out up here. So this will be the antiderivative of the secant squared of x. That will simply be the tangent of x, because the derivative of the tangent of x is the secant squared of x, and we're going to evaluate it at 0 and pi over 4. So this will just be equal to the tangent of pi over 4 minus the tangent of 0. Now make sure you know your trig. You don't want it to sneak up on you and you'll miss a problem just because you don't know your trig, even though it's calculus. So the tangent of pi over 4, that's simply just 1. Tangent of 0, sine of 0 over the cosine of 0. So 1 minus 0. And then that'll be 1. So it's really that simple. So don't forget what a definite integral is. Remember, it's the region trapped between the x-axis and the function in the in the xy plane. So like when you're dealing with evaluating definite integrals, sometimes it's not going to be so simple that you can just find the antiderivative, because let's look at number 2. We have an absolute value function. There's no general antiderivative of the absolute value of 2x minus 1. But we can rewrite this so that it is integral. So it is integrable. I don't know if that's a word. So it is able to, so we are able to evaluate this. So let me just draw a sketch of what we got going on. So we're going from 0 to 2. Now, the absolute value of 2x minus 1, this will just be, remember a V shape, where the graph, this will equal 0 when x is 1/2. So it's going to intersect the x-axis at 1/2. This is x. This is y. And when x is 0, you'll have 0 minus 1, so the absolute value of 1, which is just 1. So you're going to have this point here at 1. So your graph is going to look like this on the left, and to the right, it's going to be doing this. Now it's not drawn to scale, but we want to just evaluate it from here, 0 to 2. So we want to find this area here. So at 2, plug in 2. So this would be absolute value of 2 minus 1. So absolute value of 3, which is just 3. So it'll have a point at 2, 3. So we want to find the area of this shaded region here. So you can either use a geometry formula and find, the area of those two triangles, or you can rewrite this as the sum of two integrals. And let's just do that just so you can get some practice. So on this side of the area, this curve, or not this curve, this line is essentially going, down 1 and over 1/2. So it has a slope of -2. And so this line here is just y equals negative 2x plus 1. And then so let's look at this first. This first part will be from 0 to 1/2. And then we have negative 2x plus 1 dx that we're going to evaluate. And then we're going to add this integral, the integral from 1/2 to 2, or 1/2, yeah, 1/2 to 2. And on this part, the graph it has a positive slope of 2, and it would actually intersect, you know, the y-axis at -1 if you want to solve it. So this line would over here be y equals 2x minus 1. Whoops. 2x minus 1 dx. And then so we can actually just evaluate this. But we can also, again, find the area of just those two triangles. By evaluating this is more fun. So this will be negative 2x squared over 2. Put on my pencil, over 2 plus x. First part, we're going to evaluate from 0 to 1/2. Then we're going to add to it this integral. Let's put that in brackets. 2x squared over 2 minus x from 1/2 to 2. And then we can use the fundamental theorem of calculus here. So this is just negative x squared plus x. So negative x squared, or negative 1/2 squared plus 1/2 minus plugging 0 into here. It's just 0 plus 0, so that doesn't really do anything. The second portion, these 2's cancel again, so it's just this will be 2 squared minus 2 minus, that'll be 1/2 1/2 squared minus 1/2. And then we evaluate this. Let's see if I can fit this in. I got it. I know what I'm gonna add this sticky note here. Came prepared. So we got a negative 1. That'd be negative 1/2 squared, 1/4. So negative 1/4 plus 1/2. So that'll be 1/4. Let me make sure. Negative 1/4 plus 1/2. So 1/4 minus 0. That doesn't do anything. So plus, then that'll be 4 minus 2. 2 minus 1/2 squared. 1/4 minus 1/2. 1/4 minus 1/2. So negative 1/4. So 1/4 plus, that'll be plus 1/4. So 2/4 plus 2. Two-fourths plus 2, or just 2.5. You could say 2.5 or 5/2. Either one is fine. And there you go. It's just that simple.